My name is Kenneth De Jong. I'm an emeritus faculty member at this point at George Mason University. I've got my PhD in the 70s. I was lucky enough to be a PhD student of John Holland. They were just formulating the ideas of genetic algorithms at that time, so he, along with a bunch of his graduate students, kind of coalesced many of those ideas. From there, I took a job at the University of Pittsburgh, in the computer science department. I think of myself as a computer scientist. So my first job was at the University of Pittsburgh. I was there for about 5 or 6 years, and then I had an opportunity to help the Naval Research Lab start up what they called their Applied Artificial Intelligence Lab. And so I spent a year there, and my wife and children liked it so much, I started looking around for a job in the Washington, D.C. area, and George Mason had just decided to grow up and become a research university. And so I signed on and was at George Mason University for the rest of my career. Retired officially from the teaching side of things, but they have a very nice institute there called the Krasnow Institute, which is an interdisciplinary institute. And so I'm interacting with people who are doing biology and people who are doing chemistry, who are doing physics, who are doing neuroscience and so on. And in almost all the fields now, they're interested in computational approaches and computational models. So we're trying to blend ideas from evolutionary computation, bringing them deeper into the sciences. That's what this is all about now. Very interesting. He is a very provocative person, but he's the kind of person that would throw out ideas and then leave you to kind of figure things out. And then I would come back and say, yeah, but John, that idea doesn't work. And he says, well, that's good to know. And then he'd throw out 2 more ideas and so on and so forth. So very fascinating guy. Yeah, so my definition of evolutionary computation is that you're using Darwinian-like processes to solve difficult computational problems. So that's where I think the term evolutionary computation comes from. And I like to distinguish that from, say, population biologists or geneticists who are building evolutionary models to study evolution. That's an interesting idea, but that's not what we're all about. That is, the question is whether or not we can use these sort of ideas from evolution, Darwinian-like evolution, to actually solve engineering problems, solving scientific problems. So it has to produce answers, as opposed to just faithfully modeling data that you've collected out in the field, that kind of thing. And it actually turns out to be a very interesting dichotomy, and that is the more biologically realistic you tend to make these models, the less interesting they are from an engineering point of view. And the more you make them good for engineers, the less interesting the biologists are, because you're ignoring what they think are important details on that. So that's why I think evolutionary computation is the right emphasis. And so what is that? I think they're a problem. It's a set of problem-independent tools that can be used to solve difficult problems. So I think of them, our evolutionary algorithms, as parallel adaptive search techniques or tools. And I think of them as almost like meta-heuristics, in the sense that we think of them in an abstract way, and then we instantiate it to solve a particular set of problems. Okay? So I don't think of it as a machine learning technique, although you could say, how would you use evolutionary algorithms to do machine learning? Or I don't think of these things as necessarily optimization techniques, but you say, how would you use adaptive parallel search techniques to do optimization? So it's a tool that you can choose to apply to different things. So historically, in the quote early days, I guess you would call it shallow learning, when we had just the standard standard neural net techniques, and they would use things like backprop to tune the neural networks. Backprop are really gradient descent techniques. Well, we know very well what the difference is between evolutionary techniques and and gradient descent. And so already in the early days, people were saying, yeah, I can train neural nets using an evolutionary algorithm to tune the weights rather than using backprop, okay? And so we see the same kinds of opportunities with deep learning now. The question is, so what algorithms are currently being used? Are they gradient descent? Are they backprop-like algorithms, even at these lower levels and so on and so forth? Are there opportunities there to inject these evolutionary techniques to actually improve the state of the art? So that's how I see the two related to each other. It's not a learning tool, it's not a learning technique in itself, it's something that can amplify or enhance a particular problem area. Fun, fascination. To me, the idea of turning a process loose and not knowing how it's going to come out, and then have it come out in very interesting ways without having to sit down and tell it what to do at every step along the way. I found that just to be fascinating. Yeah, so they're not all mine, but what you discover is that in many engineering areas, if you go by the book, you have a fairly narrow cognitive approach to solving a problem. And these evolutionary algorithms don't have that, okay? So for example, we have wonderful examples of radio antenna designs which look nothing at all like the kind of thing that an engineer would build based on what he learned. They're funny shapes and twists, and they're 15% more efficient, okay? Or we have gas pipelines where you have to run a gas pipeline around a corner. And so the question is, what should the curvature look like in order to minimize the turbulence and maximize the flow? It looks nothing like what you would do if you get a textbook. So you get these rather surprising results where it explores spaces, design spaces, without the cognitive straitjacket that book learners use. But, yeah. That's really been my shtick for the last 10 or 15 years, and I guess my sense is that we have been so successful, everybody gets on the bandwagon, and everybody tries to do this and to do that, and by about the turn of the century, we probably had 40 or 50 different evolutionary algorithms and so on. And so a new person coming into the field was kind of bewildered, wasn't really sure exactly where you'd start. Or alternatively, you'd say, well, I'm a Holland student, therefore I only use genetic algorithms as opposed to something else. So the idea was, is there some kind of a unifying framework so we can talk about these evolutionary algorithms independent of particular instances of them? Think about it a little bit from a software engineering point of view, where you go up one level of abstraction and you talk about things at the abstract level, and then when a problem comes along, you start there and instantiate it to a particular problem. So that's what I've been trying to do, and that's my courses and my book and so forth are about that, of giving you that kind of higher level perspective so that you're a top-down practitioner as opposed to a bottom-up. That's a tough one because what it appears to be is that for the kind of normal problems that engineers think about that are more like optimization problems, it doesn't seem to help a whole lot. But for example, if you want to do something like, suppose you want to evolve game playing programs like a chess playing program, you need some kind of a feedback function. So what do? Do we ask thousands of people to play against it so that it learns to get better? Well, that's one possibility, and with the internet you can do that. But or alternatively, what you do is you collect somewhere the 5 best or the 10 best chess playing programs that are out there right now, and you play it against and you measure your quality or your improvement to that. Or alternatively, you have 2 populations of evolutionary algorithms, and they're playing each other. And what you're trying to do is to get an arms race going, so this one has to get better and this one has, that's the key to what we would call competitive coevolution. And then the other side of that is what we would call is cooperative coevolution. And that's the kind of thing that large engineering firms and processes do all the time. For example, if you're going to build an airplane, you break it up into teams, and they're specializing in the sub areas, and they try to do the best they can there, but it all has to be in the context of the overarching goal. So you have, with cooperative coevolution, you have a bunch of different subpopulations all working on a decomposition, a part of the puzzle, and then you have to put it all back together. I think it lies mostly, well, there are a couple of things. One is that we certainly haven't exhausted our ideas of more complicated evolutionary algorithms. So we have things called island models, and we have things called spatially distributed evolutionary algorithms and so forth. And with these sort of general characteristics, we know that they're different and they behave differently, but we still don't really understand exactly when would be the best time to use them. So there's fundamental development there, okay? But I think the biggest impact as far as the world is concerned is the ability to embed these evolutionary algorithms into other disciplines, okay? Because what we discover is that almost every scientific discipline right now, they are trying to understand their piece of the science using computational models. But they know nothing about evolutionary computation, and so the techniques that they're using are primitive by comparison. And so one of the things that we've been doing, we've been working with some biologists that have models that are trying to understand protein problems related to protein or diseases. They have computational models that take weeks to run a single experiment. And part of the reason for that, I mean, they're hard problems, so there's no getting around that. But on the other hand, some of the techniques are so primitive that by just going in and inserting an evolutionary algorithm into the right place, you go from weeks to days to hours to do the same experiment. And so that just leverages their ability to do science, okay? And so helping people inject those tools into scientific disciplines, I think. And so you're not solving big problems with evolutionary computation, but evolutionary algorithms are an engine in the middle of a more complicated problem-solving process, okay? Well, relating to what I was saying before is that I think of evolutionary computation as a tool, okay? So the question would, and a tool, so the question would be, what would be a killer app, okay? And the ones that I'm biased towards right now are the ones that I see in the sciences. So I'm working with computational neuroscientists who are trying to understand the way the brain works, and I'm working with computational biologists that are trying to solve problems of disease and so forth, okay? And in both of those cases, if we can use evolutionary algorithms to significantly improve the state of art of understanding how our brain works or how to deal with certain kinds of diseases, I think that's a huge step forward. But what you won't see in the paper, you won't see evolutionary algorithms solve this or solve that. It's embedded, in a hidden in this, but a key engine or component to the whole process. Yeah. Well, one of the things that we've been focusing on in the last 10 years or so is the relatively surprising availability of parallel computing environments. And so it turns out that these evolutionary algorithms are very easy to parallelize. but it also opens up new kinds. Once you say, I've got a parallel architecture, you can now start thinking about new evolutionary algorithms, okay? So taking advantage of this raw computational power that the parallelism gives you is something that I think is still underdeveloped in the community. And it's the kind of thing we'll need if we're going to make contributions to neuroscience or to biology or something like that. Yeah.